How's everybody doing? My name's Joe Lazarus, and the subject today is gradient descent and back propagation. Well, if you're watching this, you know I'm doing the end of semester presentation as part of a Machine Learning 2 course at SMU with John Santerre's Dr. John Santerre. All right, so throughout the semester, he breaks down some machine learning concepts, value decomposition, where we do matrix multiplication, the embedding space, graph theory, min-max flow. And then at the end of the semester, he says, now it's your turn. You learn something in depth and explain it to me. So presumably he watches, but it's likely he doesn't because he has the students watch all the videos and then vote on them. Part of the end of course project is we get voted on by the rest of the students. Watched last semester's and some of the years before, and everybody used PowerPoint. It was hard to tell who knew what they were talking about. Clip pictures in. It's not how John did it. Dr. John Santerre. Yeah, so I'm not doing it on PowerPoint. Had I not squandered all my money on booze and cheap women, maybe I'd have a Khan Academy thing where I could write on the board. And I think it's going to be a lot more fun. Learn together gradient descent. So we're going to pick a scenario with some fake numbers, give it a little backstory. And the backstory here is you're a carny predicting people's weight based on their height. What we're going to do here, I'll bring you up close to the board. You got weight on the y-axis, you got height on the x-axis, right? We're predicting weight from height. We're going to see how we can use gradient descent to optimizing your loss function. So in this case, our loss function is least squares regression. There's a number of different loss functions out there, and gradient descent. All right, so I noticed you guys couldn't really see what I was writing up on the board. So I'm going to take you to the notebook here. And at this point, you might say, hey, man, why don't you just do PowerPoint, everybody else? That's why everybody does PowerPoint. Well, maybe you're right, but I hope
this is more fun than looking at a PowerPoint. So back to our Carney example, he's able to ascertain your height, do some sort of trick, and from that he can predict your weight. This is an example where you might use least squared regression and calculate your sum squared residuals. And so what we're saying here, from the least squared line, I calculated your slope at 0.64x and your intercept at 0.948. We're just going to call that 0.95 for this example. We plot that line and we get this, and from here you can calculate your residuals, and that is your error function or your loss function. Loss function is what we want to optimize.
And okay, so gradient descent, how are we going to do that? 5 steps. You're going to take the derivative of the loss function.
Right, our sum squared, residuals.
We're going to pick initial values, plug those values into the parameter, calculate your step size. Your step size is based off the slope times your learning rate. We'll talk about the learning rate, and we'll talk about the slope that we calculated from the derivative. And then 5, you're going to calculate a new parameter, and that's going to be your next point in the grid. All right, real quick, let's talk about taking the derivative of each component of the loss function. That is what's called the grad. And you take the derivative of each component of the equation, and that's just a vector. And what you can do is have little vector r with respect to x, and this is where Professor Santerre is going to lose his, or is going to go to messing with expectation. Is this is just a matrix, and what can you do with matrix? You can have matrix multiplication, and you can move the grad along the x vector, and you can do it with y, but right now we're just holding that constant with 0. So you're going to find out how far you can move down the equation with respect to x. Grad. If we hold our intercept at 0 and evaluate
our sum squared residuals from our least squared line, we plug 0 in for the intercept, and remember we have 0.5 and 0.4, so we put 0.5 in for his height, and then we get a weight of 0.32. So maybe that's like 0.32 stone. And then we know what our true value is, right, based off our loss function. Not based on our loss function, but if we look at our loss function, you take your guess minus your off your true value, and we have 1.4 minus 0.32, and that equals 1.1 squared. And we can do that for each term in our
data set, and we get 1.1, 0.4, 1.3, and 3.1. So we can plot that our intercept, when our intercept equals 0, our sum of squared residuals equals 3.1. And we expect there to be some sort of curve. I'll draw that in. I'm bad at drawing, so in the slope. And we expect there to be some sort of minimum. All right, hey, it's Future Joe, and I was watching the video and I realized that I didn't make clear you don't typically use gradient descent on your least squares regression, but it is a useful example because we have a nice clean curve that from here and we move it up, we arrive at different points on that curve. But where gradient descent is really useful is know what your curve is going to look like. So useful is when you have complicated multidimensional problems. So response surface methodology, for example, you don't know if as you come down, if this is going to be the minimum. Sometimes this is called the local minima and this would be the global, but you don't always know if you're going to arrive at that spot. Example is in neural nets. But we're going to start with using least squared regression, plotting some different lines and seeing how that affects our derivative and the slope on that curve. So when we do go to a more complicated problem, we get a feel for what gradient descent is doing. Why you want to get the slope at each one of these points, and what's that going to tell you, right? So our local, what do we notice about the slope when it's at the minimum? It's close to 0, it's approximately 0, or it is 0. Here, if you draw in the tangent line, it's not equal to 0. As you move down this line, you're going to get closer and closer to 0, and if you go back up this line, your slope's going to increase. We want as large step sizes here, but as we approach this minimum, we want to get small steps. All right, so to evaluate this step size and find the local optimum of the intercept with respect to the sum of squared residuals, we're going to take the derivative of the intercept holding the slope constant.
The slope of 0.64x. We're going to need two rules in calculus, the power and the chain rule. If you're like me, you went to Big State University, and the person teaching the class was some grad student whose power of the English language wouldn't even allow them to order a Big Mac at McDonald's without difficulty. So this might be a useful refresher for some of us. The power rule says if you take x to the n, you can move n to the front and subtract n by 1. Right? So if you have x squared, you get 2x. The chain rule, use an example here. Let's say I have two functions, y equals x squared and x equals z squared. If I want to get the derivative of y with respect to z, with the chain rule, I can get the derivative of y with respect to x equals 2x, and the derivative of x with respect to z equals 2z, and then the derivative of y with respect to z equals 2x times 2z. And that may not be obvious, but that's actually what we're going to be doing with this loss function.
All right, great. So we're back from that refresher in calculus, and let's just remember what we're doing here. So we plugged
0 in for our intercept, and we're saying our intercept is now here, and we're calculating our sum of squared residuals, and we found that to be 3.1, and now we're looking for the slope of this line so we can calculate a step rate on that curve. The derivative of the intercept, we're first going to do is take a derivative for each one of our data points up here. I'm going to start with the first one, and then I'll do the other ones but without you guys here. So we're going to take the exponent to the front. We're going to apply the chain rule. So we're going to get the derivative of the stuff inside of the parentheses, and we simplify. That equals 1.08. Because it's a constant, we can hold that at 0. And 0 minus 1 is negative 1. We put that on the outside. We can simplify the equation, and we get negative 2. I'm not going to read it to you, but that's... All right, here's the equations for each one of our observations, I should say. It's a derivative of the intercept holding the slope constant for each one of our observations. We decided our initial value for our intercept should be 0. So if you plug 0 and then you evaluate and add each one of those up, we get these values, and it ultimately equals negative 5.7. Negative 5.7 is the slope of the tangent line to when our intercept is set to 0 for sum of squared residuals. Now, we want to use gradient descent to find a step size. Gradient descent will find a step size by applying a learning rate. In this case, we're going to set it to 0.1, and multiply the slope by the learning rate, and that equals our step size. And then we'll calculate a new parameter, and we'll get that from the old parameter minus the step size. So, if our slope is negative 5.7, we'll multiply that times our learning rate, and we get negative 0.57. We want to find our new parameter that we're going to evaluate. And if you remember, our old intercept was 0, so we'll subtract 0 from negative 0.57, and that equals 0.57. We plug that back into our equation that we found for the derivative with respect to the intercept, and this time our slope is negative 2.3. So if we think for a second, our slope's getting smaller, so we're coming down on this curve. 0.57, our slope is negative 2.3, so that's our slope. And again, we would expect our slope down here to be close to 0. All right, so what we do, we just go through the gradient descent algorithm again. We have our learning rate of 0.1. We'll multiply that by our slope, which was negative 2.3. That equals negative 0.23. And our new parameter equals our old parameter of 0.57 minus 0.23, and that equals 0.8. And we evaluate that again.
Okay, and one more time just to make sure we have it, we put 0.8 back into our equation.
For the derivative with respect to the intercept holding the slope constant, and we get 0.9. We go back to our gradient descent algorithm and we calculate a new step size, so negative 0.9 times 0.1 equals 0.09. So you can see our step size now.
The optimum, and we're getting smaller and smaller step sizes, which is just what we want to have happen. And if we keep evaluating that for a few more steps,
we wind up with 0.95, which is equal to the least squares regression line.
All right, before I do the derivatives of the intercept and the derivatives of the slope. So when we just had one variable, we were in two-dimensional space, right? We had the sum of squared residuals, and we were taking the derivative with respect to the intercept space. The three-dimensional space, we have our sum of squared residuals, our slope on that axis, and our intercept. All right, now we're ready to find the gradient of our sum of squares. And just like before, we're going to take the derivative of our sum of squares with respect to the intercept. But unlike before, we're also going to take the derivative of our sum of squared residuals with respect to the slope. And we're going to find the local minimum. If we take the derivative of our sum of squares residuals with respect to the intercept,
we use the exponent rule, and then we use the chain rule, and we find that it equals negative 1. So we simplify our terms and put it at the beginning of the equation. And then what we do is we just put in our terms into this equation.
All right, now we're going to take the derivative of our sum of square residuals with respect to the slope.
Like before, we'll take the exponent rule, we'll move that down, and we will find the derivative with respect to the slope. So we're going to treat the intercept as a constant, and we simplify, and that equals negative 0.5. So we move that negative 0.5 to the front of the equation. But unlike before, because that represents our height, right? We want to save that because that height is going to vary for each one of our observations up here. We wrote it down like that. And so just like before, what we're going to do is we're going to find a slope at each one.
Okay, if you remember, we need initial values to start with, and we're going to start with our intercept, just like last time, equaling 0, and we'll start with a slope of 1. So the
derivative of their sum squared residuals with respect to the intercept, we found that, and we're going to write it for each one of our observations. Plug 0 in for the intercept, 1 in for the slope, and add in our terms. And then we add each one of those, and we get negative 1.6. That represents the slope of the intercept on that point. And we do the same thing for the derivative of the sum squared residuals with respect to the slope. We put 0 and 1 in for the intercept and slope, and add in our terms. And we add each one of these up. So I forgot the addition sign. And we evaluate, and that equals negative 0.8. So our slope for our slope is negative 0.8. And just like last time, we calculate a step size, and we get that from our learning rate times the slopes we found. So our slope for our intercept is negative 0.6 times our learning of 0.01. And we're using 0.01 this time because point will not find the optimum. But in practice, that is something to be aware of, and it's a good thing to bring up here because you can lower your step size with each iteration of the algorithm to avoid that problem. All right, and then we want to calculate our new parameter, and our new parameter is our old parameter minus the step size. So for our intercept, 0 minus 0.016, we have a new intercept or a new parameter for our intercept, and the same for our slope.
So our old line is in pencil, and our new line is in red. And we'll repeat what we did until all the step sizes are very small, or we reach the maximum number of steps. Okay, so let's review what we learned. Step 1 is take the derivative of the loss function. In other words, take the gradient of the loss function. Step 2 is you're going to pick initial parameters to start with. Step 3, you're going to plug those parameters into the derivative equation that you find, the gradient, right? Step 4, calculate the step size. Step size equals the slope times the learning rate. You calculate your new parameter, and your new parameter equals your old parameter minus the step size. So then you repeat, you go back to step 3, continue, and you iterate through that process until your step size is very small, 0.0001, or you've reached the maximum number of steps, and that's 1,000 typically. It can depend. And that's how the gradient descent algorithm works. Of note, we only had 3 parameters in our equation, so the math wasn't that hard. If you had many observations in your data set, this type of calculation for each one of those observations could take a really long time. It could be heavy in compute. So what you might do is you take a random sample of your observations and calculate your gradient descent for that. And that is stochastic gradient descent. So you might have heard of gradient descent and stochastic gradient descent. That's all stochastic is a random sampling. What you'll see with stochastic gradient descent is instead of a slow, methodical straight line down, you'll get these kind of zigzag patterns down to the optimal value. All right, so that's gradient descent. Money on booze and cheap women.